These were where we left off last time. And so if you have this handout, we're gonna begin with this example here. Intuitively, the standard deviation, I want you to know what that means. And I want you to be able to describe differences between two data sets if one has a larger standard deviation than the other. So let's take a look at these two graphs. And looking at those two graphs, which one has the highest mean and which one has the highest standard deviation? All right, now it turns out that we can estimate the standard deviation mostly in a bell-shaped distribution, but it sometimes works in others as well. And this is just a very crude estimate. Most of the data values will fall within, a couple standard deviations from the mean. And so if you want to estimate the standard deviation, you can just take the range and chop it up into 4 chunks. Sometimes if you use the range divided by 6, that one would work. But it's just kind of a rule of thumb, and it's not very accurate, but it gives you a sense of how spread out the data are. You can use this crude approximation and use it to estimate the standard deviation. The range is also a statistic that allows us to just determine the spread in the data. Are the data very closely linked together? Or are they spread out? And if you have a large range, it's going to expand where the data values are. And the data values are going to be more widely dispersed. If the range is small, then all of the data values will be very close together. We would call that homogeneous. They're all about the same. Same thing with the standard deviation. A data set with a small standard deviation means that all the data values are very close together, like this. And if the standard deviation gets larger and larger and larger, that means there's more spread in the data. So that's what we're looking at here. And so the standard deviation and the range should be related in some way. They both give measures of spread, of dispersion. All right, so in each of these cases, let's calculate the mean. And this is just going to be an estimate. And let's calculate the standard deviation. Now, we don't have all of the actual raw data to type into our calculator. So the best we can do here is estimate. And this is a good exercise because it helps you to understand what these statistics mean. So I'll do the first one. And then I want you to do the second one and then answer the question. The mean in a bell-shaped distribution, and this is approximately bell-shaped, so is this one, is kind of right in the middle, right about right there. And for me, that looks to be 50. Now, to estimate the standard deviation, I'm going to use this little estimate here. I'm going to take the range and divide by 4. As long as I'm dividing by 4 on the other one, I can compare the two. All right, so I'm going to say that the min is 40. And here, the max is 60. Therefore, the range is 60 minus 40, which is 20. And so the standard deviation is approximately equal to the range divided by 4. So if I take that 20 and divide by 4, it's approximately equal to 5. Standard deviation of this one is approximately equal to 5. Okay, do the same thing on the next one. Write your mean and standard deviation in the chat. And then answer the question. Which graph depicts the higher standard deviation? Jason, I see your statement in the chat there. It says, I never know which group to join. So once you're placed in the group, if you hover at the very top of the window, it'll say, breakout group 1 or breakout group 2 or breakout group 3. It's not obvious. You actually have to hover up near the top of the window, and then it says 1, 2, 3, 4, 5. And then you can go click on the corresponding document corresponding to that breakout group. Anybody else want to chime in here? Looks like we have mean 52.5, 55, 55, and the standard deviation 11.25. Yeah, that makes sense. And so if you somehow go in here, you know, maybe 55, maybe 52.5. Again, we're estimating, so these numbers are going to be different. You have a max of 75 and a min of 30. So if you take that 45 and divide by 4, you're always dividing by 4, and you'll see why here as we calculate the standard deviation or consider the empirical rule. All right, so very good. So that's the first thing. Conceptually know that standard deviation increases when the data set widens, and the standard deviation shrinks when the data are more clumped together. All right, so this is another interactive one. I'm going to give you 3 data sets, and I'd like you to calculate a bunch of summary statistics, just kind of knowing conceptually what the meaning of the statistics are. So all 3 data sets, when you add up the data values, you're going to get 180. And then I'd like you to calculate the mean, median, mode, mid-range, and all of those. And no calculator, please, in your head. Here we go. Data set 1, data set 2, data set 3. In each case, we're going to have 6 data values, and they're going to be, you know, nice numbers. Imagine, if you will, that these are 6 students, and I asked, how many hours per week do you work in your job? And here's what the first group said. These 6 students. So some students full-time, didn't work any hours at all. Others are part-time, and you got, looks like 3 that are full-time, some even working overtime. The next data set is you've got 3 students that do not work at all, and then you've got 3 students that work overtime. And in the last data set, all of the students work 30 hours. Maybe these are the nursing students who are required to work 30 hours each week in their internship. Okay, that's the data set. And I'm just going to write down the summary statistics: mean, median, mode, mid-range. Again, I hope with these simpler numbers that you are able to calculate these statistics just by knowing what they mean in your head, mental arithmetic. Range, yeah, that's good. Of course, the standard deviation, I'd never ask you to calculate in your head. Oh, wait a second, maybe I'll ask you to do that in a second. All right, take a couple minutes and write down, complete this chart. I will mention that if you add up all the data values in each case, you're going to get 180. The sigma is the Greek letter that we use in mathematics to represent sum. So when I write this symbol, it means sum up all the x values, sum up all the data values. And this is important to know if you want to calculate the mean, because the mean is just the sum of all the data values divided by the number of data values. Okay, so what did you get for the mean in each of the cases here? You can go ahead and write your answer in the chat. It's always the sum of the data values divided by the number of data values. Okay, so good, 30, 30, 30. So these data sets seem to be very similar. What about the median? The data value right in the middle. It's even, so you have to average the data values on both sides of the middle. Go ahead and enter your median into the chat. Okay, yeah, so you kind of get a sense of where this is going. The medians are the same. Well, we hope the mean and the median are about the same in most distributions because they both represent the center. All right, what about the mode? What did you find for the mode? Are they all the same? or are they different this time? So you might want to write in 3 answers this time. And if a data set has no mode, then you would just say none. If a data set has 2 modes, you would write them both in. Here's how we handle the mode. It's important. The way that we're going to define it is, you look at this data set, you see 3 zeros and you see 3 60s, and then you say, oh, 0 and 60 is the mode. Over here, you see all these 30s and you say 30 is the mode. But the way we're going to define it is, in all cases, there is no mode. In order to have a mode, you have to have a data value that appears more than some other data value. All of these data values, the 0, the 10, the 20, and every other one, they appear exactly one time. There's no data value that appears more. And I think most of you got that one correct. The more subtle ones are these 2 here. That 0 right there occurs 3 times. That 0 occurs 3 times. That 0, 3 times. In all of the 60s, they occur 3 times. There is no data value that appears more than any other data value. So we say no mode. But I think if you said 0 and 60, you're kind of getting a sense of what the mode is. Same thing here. Every one of those data values is a 30, and each data value occurs 6 times. No data value appears more than 30. 30 is not the mode because there aren't any data values that appear less than it. So just a very subtle point there. Now, the mid-range, go ahead and write down what you think the mid-range is in each case. Remember, that's the midpoint between the max and the min. If you had the max and the min, what's in the middle? Mid-range. Okay, very good. Halfway between 0 and 60, halfway between 0 and 60, halfway between 30 and 30. The only number that would fit between 30 and 30 is 30. All right, in the last one, this is where you're going to start seeing some differences. So go ahead and write down what the range is for each one, and write down all 3. Okay, good. 60, 60, and 0. 30 minus 30 from max minus min. Yeah, so max minus min 60, max minus min 0. Okay, when we have a range of 0, that means that all data values fall at the very same level. So even though these data sets almost match perfectly on all the summary statistics for the center, you can see that these distributions, these data sets look quite different. This one is like uniform, 1 data value at each number. This one we would call bimodal because you're stacked at the 0 and the 60. And then this one we would just say it's kind of homogeneous. All the data values appear right in the middle. There's no spread in the data whatsoever. And so when we're describing a data set, we do want to report the center, the mean, median, mode, because that's an important number. But as you can see, we need more than just the mean and the median and the mode, because we can have data sets that match on the mean, median, mode, and mid-range, yet look quite different. So we always want to report the standard deviation as well, or the range, or some other measure of dispersion. I want to calculate the standard deviation by hand, just to show you what the calculator is doing behind the scenes. And we're going to work with some, with a very small data set. Anything that's larger than this, you would definitely want to use your calculator. Okay, so let's calculate the standard deviation by hand. Now there is a population standard deviation, and then there is a sample standard deviation. And the sample standard deviation, the variable that we use is S or SX. And the formula is, well, what we're going to do is we're going to take each data value and we're going to subtract the mean. And that's called the deviation from the mean. And it's like we're going to average those things, those deviations from the mean. Although we run into a wrinkle when we do that. Some of the deviations, if the data value is smaller than the mean, you're going to get a negative number here. And if the data value is larger than the mean, then you're going to get a positive number. And those would cancel one another out. So we do know in mathematics that if we square numbers, they all become positive. We're going to sum up all those squared deviations and then divide by 1 less than the sample size. Then to undo the squaring that we did here, we're going to take the square root. It's a very messy formula. I'm going to show you how to calculate it by hand with one of our data sets. Now the population standard deviation is sigma x. Kind of looks like an R, but it's a Greek letter. Both of those two are reported. Here, you've got the sample standard deviation, and then right next to it is the population standard deviation. You can see what the sigma sub x looks like there. The formula is very similar. We're going to sum up all the squared deviations, but instead of subtracting from the sample mean, we're going to subtract from the population mean. There's no difference in the way that we calculate the mean. And then instead of dividing by one less than the sample size, we're going to divide by the population size. Since these ends in our problems will be the same, when we divide by a larger number, the whole fraction will be smaller. So you're always going to find that sigma sub x is going to be a little bit smaller than s sub x. The population standard deviation will always be slightly smaller than the sample standard deviation. And you can see it here in our one example. You can see that this number is a little bit smaller than Sx. All right, now let's just do the hard work of calculating the standard deviation. This is the formula that we'll use. If you wanted the population standard deviation, you'd have to do it in a different way. So the first thing we want are the data values. And in our formula, we call those the x's. And we need a column or a row for every data value. So I'm going to do the data set that was our very first one in our previous example that looked like this. So here are the x's, the data values, these right here. These x's are those x's. In our calculation, we have to subtract the mean. So x minus x bar. Now, we've already calculated x bar for our data set. Those 6 data values, add them up, you get 180, divide by 6, you get 30. So this column, we're going to take each data value and subtract 30. So we get negative 30 here, negative 20, negative 10, 10, 20, and 30. You'll always find that those deviations from the mean always add up to 0. And you can see, you got a positive 30 and a negative 30, a positive 20 and a negative 20, and so on. So that's why we don't just take the deviations, the sum of the deviations, and divide by the number of data values, because the sum of the deviations will always be 0. So we have to use something else. And it's not a very interesting statistics if every time you use it, you get 0 as the standard deviation. All right, now you'll see also in our formula, after we calculate the x minus x bars, we need to square those results. So my next column is going to be the x minus x bar squared. So take each number in the previous column and square it. Notice that when we square, we end up with all positive numbers. Now you can imagine how tedious this would be if these data values contain decimals in them and the mean itself was not a nice number. It was like, 20.795 or something like that. Then these calculations would be very, very tedious. You'd have to get your calculator out. You couldn't even do them in your head. All right. Now, what we're going to do is we're going to take the sum of the numbers in this column. And the numbers in this column would be the sum of all the x minus x bar squareds. And let's see, if you, again, this is one where you can do in your head. 100 plus 900 is 1,000. Well, there's another 1,000. 1,000, 1,000, and 800. That's 2,800. All right, we're almost done. This result is 2,800. It is precisely this number up here. If you're doing the population standard deviation, it would be that number right there. So the rest of the calculation would go like this. We have 2,800 divided by 6 minus 1. And down here, we have the square root of 2,800 all over 5. Oops, all over 6, the population size. And at some point, you're going to have to get your calculator out and evaluate this. And then finally, the square root of 560 is equal to 23.664 if we just round it to 3 decimal places. And this one here would be 21.602. So now you know why I don't ask you, or most of us don't ask our students to calculate these for large data sets. Just imagine if you did a couple of those other problems by hand where you had 40 data values, you'd have to have 40 rows in this table. And then if the mean was something like, 53.796, you got to subtract, you got to square. The calculations just become too tedious. And the calculator can spit out the mean standard deviation instantly. All right, let's take a look. So it took us 20 minutes to do that problem. Let's do it with the calculator. Stat, edit. I'm going to wipe out the list and then enter in 0, 10, 20, 40, 50, 60. Get my 6 data values in there and then run the summary statistics. And here's what you should see. The SX is the 23.664, correct perfectly to 3 decimal places. And the population standard deviation, 21.602, again, perfect. So the calculator takes 30 seconds. The paper and pencil approach takes 20 minutes. This is what you'll find typically in here. And again, let me caution you not to use the paper and pencil approach, even if that's what my math lab tells you or shows you how to do when you ask for help. Okay, I'm going to ask you to do one of these. I want you to do it in your head, and I'll give you 30 seconds. Calculate the standard deviation. Create the chart to get the sum of all the square deviations, and then take the square deviations and either divide by n, 6, or divide by n minus 1, 5. Let's do the last one. It is 0. And when all the data values fall at the same place, there's no dispersion at all in the data values, the standard deviation will be 0. The mean is 30, so in every case, we're going to be subtracting 30 minus 30, and so all of these will be zeros, and when you square 0, you get 0, and when you sum up a bunch of zeros, you're going to get 0, and then if you divide by 5 or divide by 6, you're still going to get 0. So the lowest standard deviation will be 0 if all the data values fall right at the same place. And then as the data values vary from one another and you get some spread, the standard deviation gets bigger and bigger and bigger and bigger. More spread out, bigger standard deviation. All right, we use the standard deviation to help us with this thing called the empirical rule. One of the handouts for today, you see this, this graphic. It works with the bell-shaped distribution, and it's more than it's just bell-shaped. It has lots of other properties. And if it's a particular kind of bell-shaped distribution, then it's called normal. And there's so many data sets that exist in the real world that are approximately normal. We study it in some great detail. And here's what it says. The construction is going to be like this. We have the mean in the middle. We can either use the sample mean or the population mean. And then if you use a scale marking here, a lot of times on the horizontal scale, we'll use ones or tens or hundreds like this. In statistics, we use as our scale marking the standard deviation. So either use SX or sigma. It depends on, in the problem, if you're given a population set of data or a sample data set. And you just continue to add the standard deviation, and it really only requires you to add it 3 times. So go out, start at 0 and go out 1 standard deviation, 2 standard deviations, and 3 standard deviations. Do something similar on the other side, 3 other markings that are all equal to the standard deviation, like this. We call this the normal curve. Right in the middle, we're going to go up fairly high. And then by symmetry, as we go out 1 standard deviation, we're going to go up to about right here, and make sure you go up to about the same height on the other side. And then at 2 standard deviations, just going to put a value in here somewhere. If you have these points being symmetrical, then you can draw the curve a little better. But plot those points going 1, 2, and 3 standard deviations. You want the curve to be flat on the top, concave down, and then the concavity switches like this. And you want to make sure that you stay above the horizontal scale. And this is what the normal curve looks like. And it has certain properties. And the properties are that if you go within 1 standard deviation of the mean, and just remember, these curves that we're drawing, they're really curves that would go over a histogram. So we have all of our data plotted here, and it looks something like this. But underneath that nice smooth curve is a histogram where you actually have frequency data there. And we can actually count up the number of data values that fall in this range, from 1 standard deviation on the left to 1 standard deviation on the right. And what the empirical rule says is that 68% of all the data in a normal distribution like this, in this bell-shaped distribution, will fall within 1 standard deviation. And that's good, useful information. That's more than 2/3. And this is related to most things that, almost all things we study on human and plant life, or a lot of things. Now, how much of the data fall within 2 standard deviations? So if we go from here to here, 2 standard deviations away from the mean, 1, 2, 1, 2, then fully 95% of all the data in the data distribution will fall within 2 standard deviations. And finally, if you go out even 1 more standard deviation from the mean, within 3 standard deviations of the mean, you will find 99.7% of all the data would fall within 3 standard deviations. And this is called the empirical rule. Empirical is a word that we use that corresponds to delta. If someone says that's an empirical question, then that means that the question can be answered by going out and collecting data. If someone's going to test something empirically, they're going to go out and they're going to collect some data to confirm, whatever conclusion or whatever hypothesis they're making. Sometimes it's known as the 68, 95, 99.7 rule because of these percentages here. And there's all kinds of symmetry in this graph. And so if the middle chunk is 68%, then each of these smaller chunks is 34%. And if these 2 chunks have to be the same, then they have to be 13.5%. Because we want these 4 to add up to 95. And then if you go out further, this has to be 2.35% and 2.35%, so that these 2 are the same, these 2 are the same, these 2 are the same, and when you add those 6, you get 99.7. And that leaves only 0.15% out here and 0.15% out here. And you'll need to know those little slices amounts because they're going to ask you questions based on them. So you can see the same percentages here in those slices. All right, here's how they'll ask you a question. So you can see it starts off with the empirical rule. And so the first thing you're going to want to do is to draw the normal curve before you answer the questions. So SAT math scores have a bell-shaped distribution with a mean of 515. And I'm writing the population mean because I think probably they're giving us the results of everyone who took the SAT in a particular year. And then the standard deviation is equal to 114. So this is how you would then construct the horizontal scale. Right in the middle, right there, is the mean, 515. Now, the way that you number the horizontal scale is based on the standard deviation. So you're going to start adding the standard deviation. You'll add it once, twice, and 3 times to the right, and once, twice, and 3 times to the left. Calculator can do this nicely for you. If you type in 515 and then you add the 114 once, twice, 3 times, it'll give you the markings. So this would be 629, and this would be 743, and this would be 857. So we're not going to write 516, 517, 518. We're not going to write, 515, 525, 535. Our scale marking is going to be the standard deviation, and that's going to change in every problem. Going the other way, now we want to subtract the 114. You're going to have 401 and 287 and 173. So a new scale marking on this guy. Now, once you have the graph drawn, or at least the scale down here, then, you can do things like this. 68, 95%, 99.7%. So get the scale and then write those basic percentages in there. You don't have to write the percentages in there, but sometimes they help you answer the questions. Part A, what percentage of the SAT scores is between 401 and 629? What percent? See what they're asking? If you understand the empirical rule, yeah, go ahead, write your answer in there. Yeah, that's right. So they're basically these that we calculated by hand, they already knew them in advance. So the answer to this one, 68%. Now we'll get more precision later on as we do these problems, but right now we're just using the empirical rule as they told us to here. What percentage of the SAT scores is less than 401 or greater than 629? So I guess they're looking at less than 401 or greater than 629. What do you think, based on what you know about this curve? Okay, good. The most popular answer is 32. And if they ask you if these two numbers here were like part A and said between 287 and 743, then you would answer 95%. But they're saying they want you to know, they want to know this and this. And it's exactly the complement of the middle 68%. And so if the middle is 68% and the whole thing has to add up to 100%, then yes, you're correct, 32%. So use the fact that there's 100% of the data underneath the entire curve. All right, what percentage of SAT scores is greater than 743? And for this one, I will bring down the graphic here that might help you. All right, you go ahead and write these percentages in here. 34, 34, 13.5, 2.35, and 0.15. Okay, so here it says, I see some correct answers. And let's take a look. Percentage greater than 743. So here's 743. So we have to go here and over. And so that's going to capture this 2.35%. But it's also going to capture the 0.15%. And when you add those two together, you get 2.5%. Okay, so we'll practice these a little bit next time. But familiarize yourself with the empirical rule. It's always introduced in this section because it needs to know the standard deviation. And we start talking about data distributions. Okay, now we're going to go into the next new section. This is section 3.3. This is the new section for today. And in this section, we're going to calculate the mean, median, mode, mid-range, all of those things, standard deviation. We're going to redo everything that we did in the earlier section. But here's the difference. The difference is that we don't have the raw data values, the specific raw data values that we could enter into L1. We don't have those. Rather, we have a data distribution where they show us that the data are grouped in some way. And so for this particular example, homes typically are valued in a certain area based on their square footage. So the house I'm in here has 1,100 square feet. And if you wanted to buy a new house, you could estimate how much it would cost you, because in this area, it's like, you know, $200 a square foot to build a house. So if I wanted to build a 2,000 square foot home, then I would estimate 2,000 times what it costs per foot, $200 per foot, and that would work out to 400,000. So if I was trying to build a house in this area for that size, then it would cost me about 400,000. But generally, the bigger the house is, the more square footage, the more expensive the house is going to be. In this particular example, you see group data. And this is the square footage of the house. You can see the very small houses from 0 to 499 square feet. Those are tiny houses, right? You see these tiny houses on TV. Very, very small homes. But then they go up, and you can see the McMansions are down here at 4,500 to 5,000 square feet. These are big homes. They cost a lot of money to heat, especially up here. But they don't give us the specific data, but they do tell us that there are 5 homes that were this size, somewhere between 0 and 499. Now, it could be that one of the houses was 250 square feet, the next one was 300, the next one was 350, the next one was 400, and the next one was 450. But we just don't know what the exact data values are because the data are grouped, like we would do in a histogram. If we don't have the exact values of the data values, then we can't calculate the mean, median, mode exactly. But what we can do is we can estimate the mean, and we can estimate the standard deviation. And that's what we're going to do. So let's take a look. In order to estimate the mean and the standard deviation in a data distribution like this, it's a frequency distribution, right? Where you have numerical values here. What you have to calculate is the midpoint of each class. And we did this when we were looking at frequency polygons earlier. So you know how to calculate the midpoint. Just remember that we're starting at 0. And even though this class ends at 499, we're not going to write 499 on the horizontal scale, but rather we're going to write the beginning of the next class. So we don't want to stop one class at 499 and do a bar here and then do the next one like this and have a gap. We want these bars to be connected together. So this is going to be 1,000. And then we'll go to 1,500 and then 2,000. And notice we're just writing the lower class limits all the way through. So here is the midpoint. It is directly between 0 and 500. So use the midpoint formula, which is exactly the same thing as the average formula, average between 2 points, midpoint. You're going to add the 2 values and divide by 2. And I didn't need to do this calculator exercise for you to know that the number between 0 and 500 is 250. But you can see that if you're definitely going to get something different if you use 499. Now you don't want to use 499. So the midpoint of the first class is 250. And we're just going to continue to calculate those midpoints. And this is something that you need to estimate the mean and standard deviation. All right, notice that the upper class limits are jumping by 500. So the class width is 500. The lower class limits are jumping by 500. The upper class limits are jumping by 500. Hence, the midpoints will jump by 500 as well. So if you have the first one, just add 500 to it. And if the numbers were a little bit harder, you couldn't do it in your head. but you can always use your calculator. So 750, 1250, 1750, and so on. And there they are. What we're after is the mean and the standard deviation. Let me just tell you how we're going to calculate the mean. We don't know what the data values are between 0 and 499, but we do know that there are 5 of them. Those data values are probably widely dispersed in that class between 0 and 499. You might have a real tiny house that's 100 in that group that counts for one of these, and then you might have some others that are close to 500. But here's an assumption that we make as we estimate the mean. We're going to assume that all 5 of those data values in this first class are exactly 250. When we calculate the mean, we have to sum up all the data values. So it's going to be approximately the same if we multiply 5 times 250, the number in the middle, as if we actually added up the 5 data values. So we're going to estimate by using the midpoint and assume every 17 of those houses in the range from 500 to 1,000 square feet. We're going to assume every one is 750. And if we had the actual data, the sum of those 17 data values would be very close to 17 times the 750. The other thing I probably should point out is that if we did do a data distribution here, notice that the highest data values are right in here. And then as you go away from the middle, the numbers shrink. And as you go away from the middle here, the numbers shrink. So this one is bell-shaped. Here's the mean. Here's the formula. Here are the formulas for the standard deviation, both the population and the sample standard deviation. If you wanted to do the calculation of the standard deviation by hand, it would take you that table that we did before and a lot of time. So once again, we're going to use our calculator to calculate the mean and the standard deviation in this setting. And we're not going to worry about the formulas. I'm going to show you a calculator way to calculate the mean and the standard deviation to estimate. And I want to say this here because if you forget what I'm about to tell you on how to use the calculator to calculate the mean and the standard deviation of a grouped set of data, then you're going to ask for help in my math lab. And when you ask for help in my math lab, they're going to start with these formulas and they're going to work you through 3 or 4 pages worth of calculations. It's a total waste of time. So remember to use the calculator. If you use the calculator for section 3.3, the difference is going to be spending 20 minutes on the homework assignment compared to spending 6 hours. Okay, most of your problems will involve this. They'll give you a frequency distribution. You need to calculate the midpoints, and we're going to put the midpoints in L1, and we're going to put the frequencies in L2. And then we're going to use one variable statistics again. The difference is that your X list is going to be L1, and now we're going to use a frequency list that we haven't used yet to date. And we're going to put those in L2. So let's do that, and then let's use the one variable statistics to calculate the mean and the standard deviation of the group data. So I will do it here, and you can do it along with your calculator as well. You know, we can't, if you go and enter in data, you know, we can't put it a range of numbers in L1. We have to put one value, and that's why we have to go to the midpoint. So start typing in the midpoints, 250, 750, and so on. All right, then we're going to use the frequency numbers here in L2. So hopefully you can read those. You need to have as many values in L1 as you have in L2, but this is a setup. Notice that you have more than just the data values put into L1. After the data are in, we want to run the one variable statistics, because this gives us all the summary statistics, you know, not just the mean. So I'm going to quit, go back to the home screen, type in stat, go over one menu, calculate, select the one variable statistics. Now in my calculator, I don't have the menu, but if you have the menu, you want X list to be L1, and you want the frequency list to be L2. What I type in is L1 comma L2, like this. And if you have an old calculator like mine, the comma that you use is right here above the number 7. If you don't put anything in for the frequency list, or if you just do one variable statistics L1, it'll think of these midpoints as occurring just a single time. And so it'll give you a mean probably right in this range here. You know, probably 2,500. That's it. Hit enter. And here we have it. The mean square footage of a home is 2,419 in this area. And the standard deviation, SX, is 906.9642597. So we would probably round this to the number of decimal places required. Maybe it's just 2 this time because we're talking about, now this is square footage, so it wouldn't matter. Does that make sense that the mean is 2,400? Okay. Look about right in the middle here. Yeah, I don't know, somewhere in there maybe. Looks like it's a little bit lower than that. The range would go from 5,000 down to 0. 5,000 minus 0 is 5,000. If you divide that by 4, you get 1,250. Now, 1,250 would be an overestimate. So if you took the 5,000 and divided by 4, you'd get this. But if you took the 5,000 and divided by 6, you'd get this. And usually the standard deviation is between those two numbers. So if you have 7 problems, a problem like this takes you a little bit of time to calculate the midpoint and takes you a little bit of time to enter the data in into the calculator. But once you have that, you run this function and you get most of the things that they're going to ask for. And you can see this is the question that they ask here. Approximate the mean and the standard deviation. So if you have this handout, if you forget, it's just another reminder that if you're going to use the TI-84, you enter the class midpoints in L1 and the frequencies or relative frequencies, they gave us frequencies this time, in L2 by pressing stat and edit. Then after that, you calculate the one variable statistics, select L1 for the list and select L2 for the frequency list, and then enter. Okay, there is another setting, and it turns out this idea where we enter in data values into L1 and the corresponding frequencies, later on we'll enter the corresponding probabilities or percentages in L2. This whole notion of entering 2 lists, one being a frequency list, and the other one being the data list, is we're going to be calculating expected value using that approach. We have group data calculations in this section, and you'll even see raw data where you have a frequency list that you can use as well. So this approach is used frequently. And let's take a look at the way to calculate your grade. And if I can pull that up, here's another formula. And this is for the weighted mean. When you take classes and you calculate your class average, you're actually using a weighted mean. And so if you want to know how to calculate your grade in this class, all you need to know is your grades in all of the different components of the grade. So let's take a look at an example. The mathematics that you use here is no different than what we use, or the calculator functions, I should say, are no different than what we used in the previous example. So let's calculate Marissa's grade. So we'll read it, and it says attendance counts for 5%. So I'm going to create a table. You're going to need 2 columns for this table because we're going to enter one into L1 and one into L2 to do the calculation. And this looks like a messy formula here, but we're going to have Marissa's score here. That would be like the data value. It would be her scores, and what we're trying to do is to find the average of her scores. So what is the average? The average score would be her final percentage in the class, and that's directly linked to the grade. And then over here, we're going to have the weight. So if you take an exam, how much is that exam worth? Is it worth 50% of your grade, or is it worth 10% of your grade? That matters. That's the weight. The weights are the W sub i's in our formulas, and the scores are the X sub i's. in our formula. So let's read on and fill in this table. In Marissa's calculus course, attendance, right, so these weights would be what is indicated on the syllabus that each one of your grade components would be worth. Attendance counts for 5%, so we'll put that weight there. Quizzes account for 10% of the grade. Exams account for 60%, and the final exam counts for 25%. Now, you don't necessarily have to have those grades add up to 100%, but it's usually going to be the case that this number down here is the sum of the weights, and that's what appears in the denominator over here. All right, for the X's, we read on. Marissa had 100% average on attendance, so I'm going to put 100% here. She had 93% on the quizzes, 86 for the exams, and 85 on the final. Determine Marissa's course average, so her average score. So we're trying to calculate the average here. Now, according to the formula, what we would do is we would multiply these two numbers together, multiply those two numbers together, multiply those two numbers together, and multiply those together. Okay, what would that be? I don't know, something like that maybe. Then we would sum all those up, and then we would divide by the 100. Again, I want to show you how these numbers are linked to the formula, but in practice, what we're going to do is just use the calculator. So what we're trying to find the average of, our data values, that's going to go in L1, and the weights are going to go in L2. And if you want to calculate the average, you do exactly as we did in the previous example. One variable statistics, L1, L2, with the scores here. One of the things that you can notice, and then the weights here, one of the things you're going to notice is that 85%, this 60 and this 25, 80% of the grade is right around 85%, the B. So when you calculate the average, since most of the grades received 85% of the weight of the grade is based on these, only 15% is based on these high scores. So you're going to see something close to 86% here, but these might increase just a little bit. So maybe, 88%. So you can't just take those 4 grades and divide by 4 because they have different weights to them. But to actually do it with the calculator, it's pretty quick. There's not many values to enter in. So I basically replicated this on the calculator's lists. And there you see them. And I'm going to quit and run the one variable statistics again. Here's an error that students make. If I just hit enter here, it would calculate the average of just those 4 scores. Wow, my average is 91. I'm going to get an A in this class. However, that's not correct. You calculate the one variable statistics, you have to provide both the L1 and the L2. And when you do it this way, you're going to end up with that grade closer to the 85, 86. All right, so it looks like 87.15. So Marissa's final grade in the class, 87.15%.